Oh, there's the beep. Quiz for circuitry. The diagram this looked really terrifying at first, but then I said, well, you know what? When it's really terrifying, I better get my directions right. So I said, okay, looks like I have 7 amps going this way. Oh, how many amps do I have coming here? 3. How many amps do I have going out? How many amps do I have going out?
7.
Then I must have had 4 coming in. That's the only way that works. Has to have been 4 amps going through. Otherwise, how the heck could I have 7 down there? Oh, and I have 2 amps going this way. I have 4 amps going this way. How many amps must have been coming in? No. You know what? The direction is irrelevant. It's and it's towards the left, but that current really handy. Really handy. Now let's do some number crunching here. Find the current through R4. All right, well, Dueck says first thing you look for is total current. You know what? There's no current anywhere. Nowhere have they told me 2 things. I'm going to have to rewrite this as its simplest circuit. I'm going to combine all these guys into one. So it's going to be 1 over R parallel equals 1 over 18 plus 1 over 9 plus 1 over 3. And this is why I said you have to use this, because this works for 3 resistors as opposed to the one you were showing me, Olivia, that only worked for 2 resistors. And I'm lazy. I just use my calculator. I mean, if I was old school, I'd make you find common denominators and all. I did that when I was in high school. We have new technology. 1 over, oh, heck, I can even be faster. 18 reciprocal plus 9 reciprocal plus 3 reciprocal. Oh, what's the reciprocal of a half? 2. This whole thing is a 2 ohm resistor. So, what's the total resistance of this circuit? 10 ohms. 8 and 2, now in series. What's the total voltage of this circuit? 30. What's the total current through this circuit? 30 divided by 10. What'd you get, Anthony? And you know what? That is also the current going through R4. How many marks? I'd give you 1 for that, 1 for that, 1 if I saw that, and 1 for that. Now, before I turn the page, because I have my circuit here, you know what? I'm going to fill a bunch of stuff in. I'm actually, now that I know the current, going to say, okay, 3 amps. Oh, 24 volts. I times R. Why can I go 6 volts, 6 volts, and 6 volts? You want to ski? Sure. Kirchhoff's law for voltage. Any closed loop has to end up back where I started from, as long as I always go downhill. Okay, so 30 minus 24 minus 6 in any of those forks. Oh, and by the way, I could now find the current, if I really wanted to, in each of them. Current is 2 amps. I think 0.66 repeating amps and 0.33 repeating amps. Is that right? Anyways, what the heck did B want? Voltage drop. I should have asked for power. That would have been more interesting. Anyways, voltage drop across R2, 6 volts. That's why I said to you, you'd probably end up doing it to solve the other one anyhow. 2 marks? Oh, yeah. I guess I would give you 1 mark for the 24 and then 1 mark for the 6. But if you got the 6 volts, 2 out of 10. Number 3, find the power dissipated by R1. They didn't give me current anywhere. They didn't give me any starting point. I'm going to have to rewrite this. Now, this circuit is going to have 2 parallel resistor components. That one and that one. So, 1 over R parallel is going to be 1 over 14 plus 1 over 14. I think 1 over 14 plus 1 over 14 is 2 over 14. Flip it, 14 over 2. I think this is the same as a 7 ohm resistor. I said, you see there's 2 parallel chunks, Riley? You know what? I'll call this R parallel left. I don't know. Over here, I'll go 1 over R parallel to the right, which is 1 over 24 plus 1 over 24 plus 1 over 12. R parallel on the right side is... Do that one in your head, Mr. Dueck. Okay, it's 2 over 12 plus 2 over 12 plus 1 over 12. Sorry, it's 5 over 24. It's 24 over 5. It's going to be 4.8. Let's find out. 6? Are you kidding me? Dueck. It's 1 over 24 and 1 over 24 and 2 over 24. It's 4 over 24. 24 over... Wow, did I do bad math in my head? Yeah, it's 6 ohms. I'm embarrassed. So, Miller. Oh, you know what? I probably should have also said downhill, 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 downhill. Miller, what can I replace this with? A single resistor, how big?
7.
What can I replace this with? A single resistor, how big?
6.
What can I replace this whole thing with? A 7, a 3, and a 6, or as I like to say, what's the total resistance of this circuit? And what's the total voltage of this circuit? 12. So what's the total current of this circuit? 12 over 16, which is 3 over 4, 0.75. Hopefully I can do that one in my head still. It is 0.75, right?
Yep.
All righty. Well, what does that mean? It definitely means that there's 0.75 amps going here. Oh, and it means 0.75 times 3, 2.25 volts through there. Now, this is where, because these two resistors are identical, I could use a shortcut. What happens to current between identical resistors? It does split evenly. It's going to be 0.375. If you didn't know that, I'll do it the long way. But if you jump straight to that, great. I would now also say, okay, the voltage drop through here, this is the same as a 7 ohm resistor. So the voltage drop through each of these is I times R. It's 5.25 volts. 5.25 volts, and that now lets me find the current, because the current is going to be V over R, and there's my 0.375 amps. And I could find the other stuff. Carl, I'm going to quit because it said find the power. I know that power is V times I. How many volts through R1? 5.25. How many amps through R1? 0.375. How many watts do we lose? Try typing it right, Mr. Dueck. 1.97? You know what? Probably in real life, it's probably a 2-watt bulb or a 2-watt fuse or a 2-watt something. Anyways, I'll go 1.97. Is that right? And power is measured in watts. 7 marks, how would I, first of all, if you got the right answer, 7 out of 7, let's be clear. Otherwise, I would go something like this. I would say definitely 1 mark if I saw that 7 ohm, definitely 1 mark if I saw that somewhere, 1 mark if I saw that somewhere, 1 mark if I saw that somewhere, that gets you up to 4. Then I would probably go 1 mark if I saw the voltage there, that gets you up to 5. I would probably go 1 mark if I saw this, that gets you up to 6, and then 1 mark for the answer. There's your 7. Can you give yourself a lovely score out of 15, please? Really quick review. We said last day, magnets come in 2 types, 2 flavors, 2 poles, north and south. We said that magnetic fields, because we have action at a distance, magnetic fields always point from north to south. Or they always point in the same direction that a compass needle points. The symbol for magnetic field was the letter B. And magnetic field is measured in Teslas, capital T. A very large magnetic field, 50 Teslas would be very big. I showed you in a video of an MRI machine, a 4 Tesla MRI machine, and you saw that was applying over 2,000 pounds of force to a metal chair. We talked about magnetic field lines. We also said because we're going to be doing three-dimensional pictures on two-dimensional pieces of paper, we need some symbols. To show something going into the page away from us, we use X's to represent the tail feathers of an arrow retreating off in the distance. To show something coming towards us, we use dots, which is meant to be the point of an arrow coming right between our eyes. We talked about permanent magnets and electromagnets, and in fact, most of the time in this unit, we're going to be talking about electromagnets because it gives us a magnet that we can turn on, turn off, and actually, you'll learn in a bit, control the size of how strong we want the magnetic field. We said that it turns out current and magnetism, electricity and magnetism, are two sides of the same coin. Jeff, you can't have one without the other. Any wire that carries current automatically creates a magnetic field. Now, if it's alternating current, like comes from your plugs, you get a very rapidly oscillating magnetic field, which really gives you a net magnetic field of nothing because they cancel each other out, sort of. But if it's direct current, you'll get a magnetic field with a direction. What direction? We said for a wire, you point your right thumb in the direction of the current, your fingers curl in the direction of the magnetic field. Then we said you could wrap a bunch of wires together. We called that a solenoid. I said there was millions of uses. And for a solenoid, that gives you a much greater amplified magnetic field. We said if you wanted to figure out the direction of the magnetic field from a solenoid, you held the solenoid in your right hand. You curled your fingers in the direction of the current. Your thumb pointed north. Your thumb pointed north. And we paused here. Okay. Example 5. In this picture, the conductor on the left carries current into the page. The conductor on the right carries current out of the page. Okay. It says draw sample lines of force showing the direction. Let's do the left-hand one. So point your right thumbs into the page. It seems to me, Darian, the magnetic field here is in that direction, yes? Yeah. Clockwise, if we wanted to give it a circular name. What about out of the page? Well, out of the page, the magnetic field is this way. Where they are closest, right here, what can you tell me about the direction of the magnetic fields? Are they the same or opposite? Ben, I heard someone said it there. The same. And you know what? I'm going to ask you the same question. Are they like or unlike? Like. What can you tell me about like magnetic fields? What are they going to do? In this system, if you flicked this switch on, you would see the wires and force each other apart. And if you didn't have them stapled down, you could gradually, because that would happen over and over every time you turned it off and on, you could wear the ends of the wires out, cause a short, cause a loose circuit, cause the loose wire, fire bad. So they actually have to take this into account. Now again, for household circuits, because most of them are alternating current, there it wouldn't make a difference because you'd have a net magnetic field oscillating, the net field's basically zero. But for a direct current, those wires would get pushed apart. So these would repel each other. What you have just done is the same thing that's going on, sorry for those of you on YouTube, when this happens, and when Jeff couldn't push these magnets together. He tried. They're repelling. Example 6. As a review from last day, which end will be north? Try this one on your own. This is the right hand solenoid rule. Put the pen down. Hold the solenoid in your right hand, Riley. You were here. Curl your fingers in the direction of the current, which means you're either going to hold it this way or you're going to hold it that way. Those are the only two ways. One of those, your fingers will be pointing in the direction of the current. This way, yeah? Is that right? So, which is north, A or B? That's south. Now, remember, what we're really saying, because this gives us the outside of the solenoid, the magnetic field would point like this, like this, like this. It's going to start curving towards the south, like this, and you'll notice inside the magnetic field actually points to the right. I'm giving you a rule that gives you the magnetic field direction right outside. Sorry, but it's only so many rules. The tough one. What if you already have a magnet creating a field? And then you put a wire in there. When the wire runs a current, it also creates a field, and those fields will interact. The wire's field with the external field. And it turns out then that that wire will feel a force. So suppose we have a wire carrying current through a magnetic field. I guess here, since there's my battery, the current must be going this way, yes? The magnetic field will exert a force, actually quite a large force, on the moving charges in the wire. And I'll show you a video of that happening in just a second. But what we want to ask is, what's the direction? This is by far the toughest right-hand rule. This has right-hand rule number 3. It's called the right-hand motor rule because this actually explains how electric motors are going to work. And for this one, I'm going to suggest that we all use my vertical picture up here as opposed to your flat picture. So you can either hold your paper up to match or just watch up here. Here's what you do. You point your right thumb in the direction of the current. Everybody do that. Ready? Everybody do it. Put the backpack down. This is too important. Okay? Get your hands out away from your bodies, folks. Get them out. Trust me. Okay? Then, and we're going to get a little flexible here. Now, for this rule, when you point your thumb, this is wrong. You want your hand flat like you're high-fiving. Trust me. Okay? Extend your finger like this. It has to be like this. Yep. Okay? Then, step 1, point your thumb in the direction of the current. Step 2, point your fingers in the direction of the magnetic field. What direction is that magnetic field? What do those dots mean? So you're going to have to, I kid you not, go like this. Okay? Yes? Your palm points in the direction of the force. This wire is going to feel a force down the page. This is what we got. What we're actually doing, by the way, Jeff, is doing a cross product of vector multiplication. But even when you learn how to do that, you still do it with your right-hand rule. So, to find the direction of the force, point your right thumb in the direction of the current. Extend your fingers like you're high-fiving. It's okay, hand has to be flat. If you do it like this, you've added an extra 90-degree angle. Your answers are all going to be wrong. So flat. You point your fingers in the direction of the magnetic field. Your palm pushes in the direction of the net force. In the above example, the net force would be, we're going to practice a bunch of these. Example 7. You'll notice I have a wire, but I also have an external magnetic field. Which way is the current flowing through the wire? Look at the picture. Which way is the current flowing in that wire? Look at the picture very carefully. I told you in the picture. Which way? Read the picture very carefully. Which way is the current going? Please read the English. What? How do you know? Because it says current into the page. Yeah, read the picture. I'm telling you, you got to read. Okay? Sorry for being intense, but these pictures are going to be complicated. Don't just shut your brain off here. Which way is the current? Point your right thumbs into the page. Use this one. So all of you are going to point your right thumbs at me. At me. Extend your fingers. Don't be doing this. Then, which way is the magnetic field? Now, I see some of you saying, that way, don't do this, do that. Hey, you know what? Do that. Right? Cole, that's wrong. Okay, face me. Current into the page, magnetic field that way. Which way is your palm pointing? Up. The net force on this wire will be up the page. Now, if you're finding that you're having to bend weird, the easiest solution is tilt your paper 90 degrees or rotate your paper 90 degrees. Okay? Or do it upside or whatever. Can you look at the handout that I gave you? Right-hand rule questions. This puppy, please. Okay? Can you look at question 2, which starts on the bottom of the first page, but is kind of on the right-hand side? This. Okay? The reason I barked at Darian is there's going to be arrows in all sorts of directions. You can't just look at the arrows. So very carefully study this picture. Is there a wire carrying current? Yes or no? Yeah. Is there also an external magnetic field? This is the third rule. All of you point your right thumbs in the direction of the current. Now you can either use mine or you can use yours on I don't care. Now stop. I still see some of you starting out like that. Get this rule right away. Get the hand out like you're high-fiving. Which way is the magnetic field? To the? On mine, to the right. So if I was holding my paper this way, I would point my thumb like this. I would extend my hand like this. Which way is my palm pointing? Is the answer A, B, C, or D? C. Into the page. Yep. Oh, you're just doing it up high? Okay, that's... We're going to practice this a bunch. Number 3. Now, instead of a current in a wire, I've just got a proton moving. But you know what? A proton moving, that's what's happening inside the wire. That's like a current. So, which way is the proton moving? Kind of up. Now, hang on. See the two magnets? What direction is the magnetic field between them? Magnetic field lines always point from what to what? So all of us right now, every one of us, let's add the magnetic field lines pointing from north to south. And here's what we have. Which way is this proton traveling? That way. Which way is the magnetic field? Which way am I going to point my fingers? That way. Is the answer A, B, C, or D? Sorry? D, towards the South Pole. My palm is pointing towards that.
Bottom of the page.
Bottom of the page. B. This is how particle accelerators work. If you're wondering, how do they make those charges go in a circle? Magnetic deflection. Got more? Come back to that in a second. Come back to that in a second. Number 11, which I think actually shows up here. Number 11, which kind of shows up on the, half of it shows up on one page, but the full question shows up here. Proton, see it? Proton, positive, conventional current. Which way is the proton moving? To the right, so point your thumbs to the right. It's moving along happily, and then all of a sudden, whap, it runs into a magnetic field. Which way is the magnetic field pointing? So which way will this be deflected? So for me, if I'm facing my diagram, boom, boom. Oh, A, B, C, or D? Which, are you using that, or are you using this? Then hold your paper up. That, first of all, give me the paper. Hold your hand. Don't move your hand. You're telling me that that magnetic field is pointing that way. Those X's, it's pointing that way. Got to go like that then. Right, guys? Sorry, I'm really intense today. I don't know why. I'm not mad. I'm not! Okay. People on YouTube are freaking out. So, either use this one or use your paper, but don't use both. So, Darian, let's use this one. Ready? Get your hand up. Yes, yes. C. Yes, toward the top of the page. Go back to our notes for a second. Protons are great, and we can move protons around, but the easiest particle to move are electrons. You're going to be asked a lot of electron deflection questions. Well, example 8. An electron traveling to the right. Can you underline electron traveling to the right for me, please? That's important. We don't have a rule for electrons. Our rule works for current, and current is positive. Well, an electron traveling to the right is the same as a proton traveling which way? So you can make a little note here, same as P plus to the left. So if I ask you this question, although the electron is going that way, the proton, Jeff, is going that way, what direction is that external magnetic field? What do those X's mean? Okay? So, are you going to use this or that? Which one? You use this? Okay? No, you're not. Ha. Not going to let you, because you need to get used to using it for your own homework anyways. Now, by the way, I find holding it up does help. Gives you just a more three-dimensional. Good, which way? You're going to point your thumb which way? Not in the same direction as the electron, the opposite direction of the electron. Are all of you pointing your palms down the page, I hope? Yes? It's going to get deflected down the page. Back to the right-hand rule handout. I skipped an electron question. Sure, number 5. Number 5. All of you underline the word electron. I don't deal with electrons. And again, this goes back to my rant of all that time ago about Ben Franklin. Boy, did you screw up by calling these positive and these ones negative. You really did. Anyways, an electron traveling to the right is the same as a proton traveling which way? So I'm going to point my thumb to, first I need the direction of the magnetic field. I see a north pole, I see a south pole. Magnetic field lines always point from what to what? Let's draw in a couple of external magnetic field lines. Which way will this electron be deflected? No. Proton traveling that way. Okay, I got to bend a little bit. And for me, I'm getting out of the paper. Yeah? Oof. Out of the paper. Straighten your hand. You got a kink. Straighten your hand. Yep. Yeah, tilt your elbow up. If you have to, elbow Anthony in the head. We got a few more. Yay. Number 12. A wire between two magnetic poles is shown in the above diagram. You know what? Which direction is the magnetic field caused by that big horseshoe magnet? Magnetic field lines point from what to what? There's the external magnetic field. What direction is the current in that wire? Go look at the battery. I think the current is going this way, then this way, and in the bottom wire, I think it's going that way. Right? Point your right thumb in the direction of the current. Extend your fingers so that all four are pointing in the direction of the magnetic field. You'll find it easier to put your pen down if you're right-handed. Otherwise, your hand's going to be at a wonky angle. Trust me, Riley, I've done this before. A, B, C, or D. Try circling this one on your own. Let's see. Current? Yes? Magnetic field? Okay. Okay. Now here's probably where I would choose to maybe turn the paper or something, but I'm getting B, down. Number 13 is cool. Number 13 is cool. What if we put a circular coil of wire inside a magnetic field? Well, on the top, what direction is the current pointing at the very top of that circle? Don't overcomplicate it. On the top of that circle, what direction is the current pointing? To the left. Point your right thumbs to the left, please. What direction is that external magnetic field? What do those X's mean? Okay, so the top is going to feel a force in which direction? Down? Draw a little arrow like that. What about the bottom? Which way is the bottom current traveling? To the? So point your right thumbs to the right, also extending your fingers into the page. Which way will the bottom of the wire feel a force? By the way, right here, the current is pointing up. So how about, can all of you point your right thumbs up? Magnetic field into the page. Which way will this experience a force? And hey, this is how you could build an electronic compression or shrinking machine. It's going to contract. It's going to do that. Flip the current, and you would see this circle of wire get really tense as it wanted to get as wide, as big, as large as it could. Number 20, which is partly on one, but here, this one. So, where do we apply this? First of all, we use this when we're studying subatomic particles just to separate them and figure out which ones are positive and which ones are negative, because positive and negative charges will be bent in opposite directions. So here is an example. We have a beam of positively and negatively charged particles. Oh, if we send them through a magnetic field, we can separate them. So the beam is traveling to the right. Let's assume they're positive. Point your right thumbs to the right, please. What direction is the magnetic field? Into the page. What direction will the positives be deflected? What direction will the negatives be deflected? So, which is the positive? Yes, yes, no, no. Which are the negatives? No, yes, no, yes. And there, you're doing particle physics. The very beginning of it, but step one. Hey, here's how I can separate charges by their polarity. Back to our notes. Oh. So there is a force acting on a wire. How big? Oh, first let me convince you that the force does exist. Put your pencils down. Have I convinced you that there is a force? I hope so. How big? That's the next question. Here is finally our first set of equations. It turns out that the force on a moving charge depends on three things. Oh, let's use it. So I usually call this FB for magnetic force, as opposed to FG for gravitational force, or FF for frictional force, or FN for normal force. Okay? It depends on how big the charge is. If you're just moving a charge, we're going to get to a wire in a second. But if you're just moving a charge, depends on how big the charge is, if you're just deflecting a charge. It depends on how fast it's traveling, its speed. And it depends on the magnetic field. Except These have to be at right angles to each other. Otherwise, your right-hand rule thingy doesn't work. They have to be, it turns out, it's only when a charge is traveling perpendicular to a magnetic field that it feels a force. If it's traveling parallel to a magnetic field, it feels no force. Sometimes the charges don't move perpendicular. If that's the case, you've got to use the component. In fact, you'll often see it written this way. Q, V, B, sine theta. Jeff, we're not going to deal with that. I showed it to you, but we're not going to deal with that this year. So, it turns out if you have a magnetic field line going this way, so here's my B field, and you have a proton traveling parallel to the field, it will not experience a force. It's only when it cuts across the magnetic field lines, that's when it starts to experience a force. We've been able to demonstrate that in labs again, in experiments again and again and again and again and again. So, if theta is 0 degrees, you would get this. F equals Q V B sine 0, sine theta, sine 0. What is the sine of 0 on your calculator? You get no force. Sine of 0 is 0. 0 times B times V times Q. Doesn't matter. It's 0. Oh, and if theta equals 90 degrees, you get the maximum force when they're perpendicular. And we are only going to deal except once. I may give you a situation where they're parallel and expect you, Trevor, to say, oh, force is 0. Like, if you go back to the right-hand rule handout, this one here, number 21. See the electron? Which way is the electron traveling? To the right? I don't deal with electrons. Which way is the mathematical equivalent, a proton, traveling? To the? Okay. Which way is the magnetic field? Now the answer here is going to be this electron is going to feel no deflection, a linear path. And you can also try it, because if you try going with your right-hand rule, Mr. Dueck said keep your fingers extended. He said you can point your thumb in the direction of the current. How can you point your fingers in the direction of the magnetic field? It doesn't work. Doesn't work. Pardon me? Well, you can do that, but now you got the current in the wrong way. Really, you'd have to do kind of that, but that's not how I've taught you. It's like you're shaking hands or high-fiving someone. This is this is the right-hand rule, the right-hand motor rule. Let's crunch some numbers. A proton is moving at 1.7 times 10 to the 6th meters per second. It enters a 0.15 Tesla magnetic field. Here's the important part. At right angles to the field, they are perpendicular. What's the net force on the proton? And what's the net acceleration? You know what, Jeff? I'm going to call this part A, and I'll call this part B, and let's do part A. What's causing the force here? A magnetic field is exerting the force. And the force on a moving particle is QVB. Q, it's a proton. Oh, we've heard that dance before. (1.6) times 10 to the negative 19, I think, yes? If you said 7, I think you were giving me a mass in there somewhere. Okay. V, 1.7 times 10 to the 6th. B, 0.15 Teslas. That's a big magnetic field. How many newtons of force? You get 4.0. Am I wrong?
No, I just had a quick question.
I have a quick answer.
0.15 to 0.15
Teslas, that's the new magnetic force field unit that we learned last class when you were away. So magnetic field is measured in Teslas, the same way electric field is measured in newtons per coulomb, the same way gravitational field is measured in meters per second squared or newtons per kilogram. Magnetic field is measured in Teslas, named after a scientist whose last name was? Very good. It's the second last unit that you'll learn in Physics 12, Jake. There is one more. 3 lessons from now. Now, what did we just find? A force. Force is still measured in what? There. Now, that may seem like a very small force, Anthony, but what does part B want me to find? Hey, if I know the net force, how can I find acceleration? What's the equation that has those in it? Can you get the A by itself for me, please? Which F? 4.08 times 10 to the negative 14. Which M? It's a proton. It's on there somewhere. 1.67. I missed the times 10 to the negative?
Negative 27.
27. Divided by 1.67 to negative 27. And you get a pretty stinking big acceleration. 2.44 times 10 to the 13th. 2.44 times 10 to the 13th meters per second squared. Or if you divide by 9.8, I think it's several trillion Gs. Can we go back to the right-hand rule handout, please? We're going to practice some more. Number one. Number one. 2 particles, X and Y, of equal mass, let's underline that, I bet you that's important, but different charge enter a uniform magnetic field with the same velocity. Which of the following best compares the statements? You know what? First, let's figure out which one's positive and which one's negative. Which one do you want to look at, X or Y, Anthony? Let's assume it's positive. Let's point our thumb in the direction it's traveling. You got your, okay, I think your thumb is pointing that way, isn't it? No. Right here. Not after, at the beginning. It's the other stuff is showing you how it got deflected. So to the right. What direction is the magnetic field? Into the page. Which way will a positive charge get deflected? Up. And okay, so you know what? X is positive. What can you tell me about charge Y since it got deflected down? What must it be? Negative. So that could be good. Yes, yes. No, and no. Now, the force on a charge is equal to that. They have the same mass. They have the same velocity. So, did they follow the same size deflection? Look at the picture. Did they follow the same size deflection? Nope. That means one of these has a bigger charge. Which one? The one that got deflected the most. Which one got deflected the most? And this is counterintuitive because I heard somebody say, well, why? Why is in a smooth sweeping curve it didn't get deflected much at all? Which one got deflected into a tight curve? X. Which one has a bigger charge? X. Yes, no, yes, no. There's a lot you can do with right-hand rules and the knowledge of this equation. Number 7. Okay. The solution in the tank above contains positive and negative particles which move in the directions shown before the magnetic field is switched on. So if you all look up, initially the positive charges are attracted to this negative electrode, and the negative charges are attracted to the positive electrode. Then we turn the magnetic field on. What's going to happen? Let's look at the positive charge. Which way is it moving before we turn the magnetic field on? To the right. So let's point our thumbs to the right. What direction is the magnetic field? Which way will the positives get pushed? Okay, so positive particles are going to get pushed. Yes, yes, no, no. What about the negatives? Are they towards the bottom? Well, let's see. What direction, before we switch the magnetic field on, are those negatives moving? To the? We don't deal with negatives. Negatives moving to the left are the same as positives moving which way? So point your thumbs to the right. Which way is the magnetic field? Oh, which way will the negatives also get pushed? And the reason is they were starting out traveling in the opposite direction. They're also going to get pushed. Now, really what's going to happen, if you all look up just to show you an application, is this. Positives will get pushed this way, negatives will get pushed this way, and what you'll actually have is you'll have created some kind of a convection current. What you have is something that can stir liquid with no moving parts. That can be handy. It'll stir stuff without actually having any blades or spoons, but it'll stir it. Kind of cool. Correct answer B? Yeah? Number 8. When a certain proton enters a magnetic field as shown above, it follows path P. That's this one here. By the way, what shape is this proton tracing out? A circle. Mr. Dueck, does that mean we're going to be able to say magnetic force equals circular force? Preview of coming attractions. But yes. Mr. Dueck, is that why when they build particle accelerators like the Large Hadron Collider, they build them in the shape of a? Now you know. Okay. So there's the proton. An alpha particle, which has twice the charge and 4 times the mass, which path will it follow? Alphas are positives, so first of all, I know those are wrong. I remember alpha particles are positive. In other words, I would cross out those two. Now, if it had twice the charge, it would deflect even tighter. Oh, but what else does it tell me? 4 times the speed. Read carefully. Okay, 4 times the mass. You know what? That's going to make it tougher to deflect. Now, if it was twice the mass and twice the charge, the path would be identical to path P. Because the twice the charge makes it bend faster, but the twice the mass makes it twice as hard to bend it. Which one's making a bigger difference? 4 times the mass, it's going to be tougher to deflect. Q. That's getting, we haven't learned enough to really wrap our brain around that yet. think we've done most. Oh, here we go. Number 15, which is for some reason over here. An electron traveling at a high speed enters a magnetic field as shown. That's the first picture. By the way, which way does the electron get deflected? Down the page? You know what, then? Protons aren't going to be any of those, are they? Because protons are oppositely charged. So it says, which 6 choices best illustrates the path the proton will follow? I can already tell you it's R or S or T. What can you tell me about the charge of a proton? Bigger, smaller, or the same size as an electron? Same, okay. What can you tell me about the mass of a proton? Bigger, smaller, or the same size, same mass as an electron? Bigger, so it's going to be tougher to deflect. So R, S, or T, which one? T. B says, using principles of physics, explain. We just did. We're going to pause. Your homework is study for the test.